Sorun girdi. Sünni.
Good afternoon, dear participants.
Hello.
Hello. Can
Hello.
you hear me?
Yes.
Yes.
Okay. Good afternoon, everybody. Welcome to the session 22, Electrical Machines 2 session of the 13th International Conference on Electrical and Electronics Engineering. Due to COVID-19 pandemic conditions, we are unfortunately having the conference via online platforms. And I would like to introduce myself first. My name is Professor Lale Ergene, and I am from Istanbul Technical University Electrical Engineering Department. I'll be leading this session as the conference chair. And today we will be having 4 papers to be presented. Each presenter will have 20 minutes, including questions and answers. If you have any question, please write on the chat, and I will ask to the presenter end of the presentation. Let's start with the first presentation. The name of the paper, the title of the paper, Detection of Eccentricity Faults of Induction Motors Based on Decision Trees. The authors are Eyup, Irgat, Abdurrahman, Unsal, Huseyin, Tayyer, Canseven. They are from Kutahya, Dumlupinar University, Turkey. Eyup Irgat will be presenting, and I would like to ask him to introduce himself briefly beginning of the presentation. You can upload your presentation, open your presentation, please.
Hello everyone. My name is Eyup Irgat. I am PhD student at Kutahya Dumlupinar University in Turkey. Today, I am going to talk about detection of eccentricity faults of induction motors based on decision tree.
We don't see your presentation on the screen. Could you please upload?
Me. Can you see?
Yes, we can see right now. You can continue. Thank you.
Yes. Induction motors are widely used in all areas of applications with motion in modern world. Induction motors are used in heavy conditions and therefore are subject to various mechanical and electrical faults. Induction motor faults are divided into 2 groups as electrical and mechanical faults. Electrical faults include rotor faults and stator faults. Mechanical faults include air gap, eccentricity faults, bearing faults, and misalignment. One of the common faults of induction motors is the eccentricity faults. The faults of induction motor are not independent from each other. Some types of faults, such as rotor faults, may lead to a secondary fault in the motor. For instance, vibrations on the shaft due to broken rotor bars or eccentricity in the air gap may lead to bearing faults. Therefore, detection, diagnosis, and classification of faults of induction motors are important to prevent costly failures. Excuse me. Therefore, detection, diagnosis, and classification of faults of induction motors are important to prevent costly failures, avoid expensive economical losses, prevent unexpected downtime, and provide maximum uptime in production. The bearing faults have the largest ratio among the total faults of induction motors, as it can be seen from figure. One of the main effects of bearing faults of induction motors is the eccentricity in the air gap of induction motors. In this study, the eccentricity faults of a 3 kilowatt induction motor were analyzed by using decision tree method. Machine learning based classification methods are used in a wide array of applications, including classification of faults of induction motors, artificial neural networks, principal component analysis, support vector machines, k-nearest neighbors, k-means, random forest, and decision tree are commonly used machine learning methods. In this study, decision tree method is used to distinguish the healthy state of an induction motor from the eccentricity faulty state by using vibration signals. The imbalance of the air gap distance between the stator and the rotor of induction motors causes the eccentricity faults. Eccentricity faults can be classified as static, dynamic, and mixed eccentricity faults. Static eccentricity faults usually caused by assembly faults or oval-shaped rotors. The graphical representation of eccentricity faults is given in this figure. Dynamic eccentricity faults may occur as a result of the bending of the motor shaft, wear of deterioration of bearing, or mechanical oscillation of the motor at certain critical speeds. Static eccentricity faults may cause the air gap magnetic field distribution to deteriorate, resulting in bending of the motor shaft and lead to dynamic eccentricity faults. If static eccentricity faults continue, the rotor can rub to the stator and cause damage to the stator body and or winding of the motor, therefore result in complete failure of the motor. The eccentricity fault was implemented in laboratory by expanding the bearing housing in the end shields of the induction motor. The rotor rotation center was shifted by 0.2 millimeters. Two bushings were designed and produced from PLA material by using a 3D printer and placed in the expanded bearing houses at each end shield of the motor. The schematic of the experimental testbed used in the signal collection is given in this figure. The testbed consists of a two-pole 3 kilowatts induction motor, a 5 kilovolt ampere self-excited synchronous generator loaded with a variable resistive load, a 3-axis accelerometer, and data acquisition system. In the first case, the motor was tested in healthy condition. In second case, the motor was tested with eccentricity valves. The three-axis vibration signals of healthy motor and motor with eccentricity fault were collected. The three-axis vibration signals were recorded with a duration of 41 seconds. The time window for each record is taken as 0.1 seconds. The statistical features including peak-to-peak RMS, skewness, kurtosis, stress factor, and mean values are extracted for each time window. The distribution of statistical parameters of three-axis vibration signals were evaluated by using the box plots. The box plots used to compare the distribution of the statistical of z-axis vibration signals are given in figure. Class 1 represents the healthy motor, while class 2 represents the eccentricity faulty motor. It can be seen from the box plots of the z-axis vibration signal that the peak-to-peak and RMS values of eccentricity faulty motor are higher than those values of healthy motor. The same analysis was also performed for the x-axis and y-axis vibration signals, but not presented graphically due to the limited number of pages. The scatter plots of statistical features of z-axis vibration signals. It can be seen that the distribution of each statistical feature is in agreement with the results presented in box plots. The results show that the statistical features extracted for each axis vibration signals can distinguish a healthy state of the motor from a fault state. The confusion matrices obtained with decision tree classifier belonging to vibration signals of z-axis statistical features, including peak-to-peak RMS, skewness, kurtosis, stress factor, and mean value are given in this figure. The higher accuracy rate of 100% was achieved with RMS, while the lowest accuracy rate of 58.94% was achieved with skewness in
I think there will be disconnection, so I cannot see the presenter on the panelist right now. He's trying to connect again, I guess. I'm sorry for the interruption. We are waiting the entrance of the presenter. I'm sorry for the interruption. The presenter is disconnected. We are waiting for him to connect again. Yes. Welcome back. We cannot hear you. You are muted. Yes. You can leave your camera on actually, please. Since you are presenter, you can leave your camera on, and I think you disconnected. You can upload again and continue your presentation, please.
Yes. Nerede kaldılar? Can you see?
Yes, we can see your presentation now. Conclusions.
Conclusions. A simple machine learning algorithm decision tree is employed to distinguish the faulty motor. The results show that the decision tree classifier can be used to identify the eccentricity faults of induction motors with an accuracy rate of nearly 100%. Thank you for your patience.
Thank you very much for tonight's presentation. I cannot see any question on the chat board. Is there any question you can write? Meanwhile, I may ask a question. These vibrations you are collecting are only the mechanical vibrations?
Yes.
Did you consider any magnetic vibration, or did you try to separate them? Did you do any study for that, like doing double FFT?
No.
Okay, thank you.
Thank you.
Okay, we don't have question more, so we can pass to second presentation. The number 56, the presentation ID, and the title of the paper is Determination of Optimum Stator and Rotor Resistance Values for Obtaining Parameters of Three-Phase Induction Motor with Taguchi Method. The authors are Murat, Toren, Hakki, Mollahasanoglu from Recep Tayyip Erdogan University, Turkey. And our presenter is today Hakki Mollahasanoglu. You can present your paper, and please start with a small introduction about yourself. Thank you.
Thank you, Professor Ergene. Okay, can you see this presentation?
Yes, we can see your presentation, please.
Okay, thank you. Hello, everybody, and welcome to my presentation. That's determination of stator and rotor resistance value for obtaining parameters of three-phase induction motor by Taguchi method. And I am Hakki Mollahasanoglu and PhD student, and I am preferred this study together with Murat Toren. This presentation includes for title 1 introduction. In this section, we talk about purpose and importance of our study. And 2 method. In this section, there are induction motor design and description of the Taguchi method, findings and results, and finally, conclusion. As you know, induction motors are electrical machines widely used in the industry, considering their cost and operation principle which meet most needs. Studies are conducted on increasing the working efficiency of induction motor and energy efficiency of drive systems. And design parameters must be selected at optimum value for induction motors to operate efficiently. For this purpose, different design parameters are optimized, such as motor widening parameters, motor slot tip, and widening tip, etc. And of course, optimization methods are used for this, like genetic algorithm, particle swarm optimization, and find element method, and etc. But in this study, Taguchi method be used for optimization of induction motor, stator, and rotor resistance parameters. Although the Taguchi method is a statistical method, frequently used in product manufacturing, biotechnology, etc. There are many studies using Taguchi method in electrical machine application in recent years. These can be drive systems and motor applications. But this method is still less well known in electric machine design applications. In this study, it's aimed to optimize the stator and rotor resistance values of a three-phase induction motor with the Taguchi method. For this, four control parameters which are related to the motor power are selected. And these parameters are utilization factor, magnetic flux density in the air gap, and flux density shape factor depending on the magnetic saturation of the teeth and pole spacing. These parameters are analyzed using the Taguchi method, and optimum stator and rotor resistance values are determined. Second, ANOVA analysis is performed to determine the effect of each control parameter. Induction machine design can be realized using different design methods, which have been investigated. The most accurate method among these methods is evaluated as the design method, made by using the manufacturing parameters. And the equations used in the machine design and whose importance are specified in the design are shown in this slide. Here, KV is widening factor. Among the parameters in this equation, C0 and BN and tau and alpha 1 parameters that affect motor performance and take values at certain intervals are determined as design variables. Appropriate values ranges of these parameters are determined for the 116 kilowatt three-phase induction motor to be designed in this study. These values obtained from R1 and R2 represent the stator resistance and rotor resistance, respectively. These resistance values affect the power expansion you see in equation 1. This effect is important to obtain optimum parameters in motor design. And Taguchi method. Taguchi method was developed by Jenichi Taguchi in the 1914. The most important feature and advantages of the Taguchi method, unlike other methods, is that the method simplifies in the experiment plan and greatly reduces that experiment's number. This feature shows the Taguchi method is a good technique that produces an efficient and systematic methodology. These figures summarize the Taguchi method steps. In addition, in Taguchi method, variance analysis is performed to see the significance of the process parameters. This is a statistical analysis is known as ANOVA. After this analysis, the optimum value is calculated from the experimental result. And first of all, first the data sheet of the three-phase induction motor used in this study are given in table below. As you can see, voltage and motor input voltage 380 volt and output power 160 kilowatt, nominal torque 1029 Newton meter, and efficiency 94%. The analysis of this experimental study was done using Minitab software. In order to obtain optimum parameters of three-phase induction motor, four main control parameters have been selected. These parameters are the utilizing factor or efficiency constant, that means C0, and magnetic flux density in the air gap, flux density shape factor dependent on the magnetic saturation coefficient of teeth, and pole pitch. 5 levels are assigned for each factor. The factor and levels selected for the optimization of induction motor parameters with the Taguchi method are shown in table 2. And the selected level values written according to reference Mr. Bodrolu and induction motor design. The experimental orthogonal array for 4 control parameters generated using L25 in Minitab software is shown in table. In the traditional motor design method, re-experiments are required as each factor level changes. This means doing at least 625 experiments for this study. But the orthogonal array treated by Taguchi method are calculated only 25 times. It is sufficient. Thanks to orthogonal array, the computation time is greatly reduced. SNN Russia response, that means as signal and noise Russia response table calculated by the Minitab software is given in table 4. The factors that have the greatest impact on the response are determined from this table. And the delta value given in table is the difference between the highest average response characteristic value and the lowest average response characteristic value. The factor with the highest delta value is the first place. This means that it has the most influence on the response. The response graph of the SN ratio of the factors obtained by orthogonal array experiments with Minitab software is shown in figure. In this graph, the x-axis shows the factor levels and y-axis shows an SN ratio. After the response table has been created, the prediction is made for the optimum state. In other words, the suitable levels determined for each factor. And table 5 shows the most suitable levels for each control parameters. For example, for factor alpha 1, the optimum value is 1 and for level 5. Using the optimum motor parameters shown in table 5, the stator and rotor resistance values R1 and R2 of the induction motor have been optimized. The new values obtained or shown in table 6. The motor performance values are predetermined by using the stator and rotor resistance values optimized by the Taguchi method. The results are as in table 7. As can be seen from table 7 compared with the Intel design, and the efficiency increased by 4.25% and after Taguchi optimization, and change of about 1% in torque value is calculated. However, this can be ignored according to the effect of stator and rotor resistance values on efficiency and power expansion depending on efficiency. The slip value, on the other hand, can be taken as the same since it shows negligible variation. In this study, ANOVA analysis was conducted to examine the contribution rates of the selected control parameters in detail. The results of the ANOVA analysis are shown in table 8. As can be seen in table 8, alpha 1 value is determined to be 16.30% effective on the analysis made in the experimental study. And the secondly, BN 36.90 contribution. According to experimental design principle of the Taguchi method, if the p value is less than 0.05, it shows the factor has a significant effect on the experimental results. That's the factor is an important factor. In this study, it's aimed to optimize the stator and rotor resistance value of three-phase induction motor with the Taguchi method. In this method, the catalog value for R1, and this means stator resistance, and is 0.0063 ohm. It's decreased to 0.004 ohm. It means to 3 to 6% lower value. Similarly, the catalog value for R2 is 0.0083. It's decreased to 0.0068 ohm. Namely, it is 18% lower. The obtained low resistance values are important for machine nominal power value, which is effective in machine performance. For example, as can be seen from table 7, compared with the initial design, the efficiency increased by 4.25% after Taguchi optimization method. Thank you. Thank you so much for listening.
Thank you very much for the nice presentation. Is there any question we can have right now? ANOVA is analytical calculation program or numerical calculation program? I didn't understand that.
ANOVA is numerical analysis program.
Have you get a chance to show any torque distribution? Are you getting the desired torque with reduced resistance values and with these optimization?
Tables 7 and torque there, torque until 1029 and Taguchi 1020.
It seems to me the efficiency values is quite high for induction machine, but are you using specific material for that, or you are using conventional material? What type of material did you use as a lamination material?
I understand. I don't understand.
Did you use like M700, like classical material for the B values, or you have used special material, like new generation material?
No, another different materials. Yes.
Okay, thank you very much.
Thank you, Sandra.
We can pass to third presentation. The
Hello?
ID.
Yeah, I think it's 64,
Yes.
right? It's Berk,
Yes,
yeah.
it's 64. The idea of the presentation is 64. The title is Analysis of Driving Cycle with Wireless Communication in Electrical Vehicles.
Yeah.
Berk Bilgin will be the presenter and the author of the paper. He is from AVL, Turkey.
Yeah, let me share my screen.
Please.
Can you see now?
Yes, we can see your screen.
Yeah, okay. Firstly, let me introduce myself. I'm Berk Bilgin. and I am working in AVL Turkey as a senior system engineer on electric vehicles. And today my topic is the analysis of driving cycle with wireless communication electric vehicles. Yeah, the today content is contain 5 different topics. I will start with the introduction to introduce you my goal of the, let's say, research, and also main idea of the electric vehicles. And after that, I will try to introduce you the vehicle network architecture and the architecture that we were using in this project. And yeah, and the integration phase of the wireless gateways to vehicle is the third topic, and the analyzing of the measurements of the wireless communication is the fourth one. And then I will finish with the conclusion with the outputs of the project. Yeah, mainly today, you know, the electric vehicles become much more popular than the previous years, because in the countries, in the different areas, there are different concerns on their environmental concerns, on fuel consumption, and therefore the electric vehicles become much popular today. And actually, the transportation is the you know, the electric vehicle technology is more, let's say, older technology than the internal combustion engine vehicles. As you can see, right hand side, maybe I can. In right hand side, this is the one of the early electric vehicles at, I think, 1890s, and this is the let's say the first transportation vehicle maybe. And yeah, this technology is older than the internal combustion engine, but you know, the safety concerns, or the, you know, the range efficiency or the cost of the vehicles is let's say not let's say competitive with the internal combustion engine. Therefore, in the 1990s, beginning of the 1990s, the combustion engines are, let's say, only let's say technology that we are using for the transportation. But according to environmental concerns and the beginning of the 2000s, and the electric vehicles, and also therefore the hybrid vehicles, become more let's say popular in our life. And as you can see there, today is the most biggest problem in the electric vehicles, as you know, the range of the vehicle and also the cost of the vehicle. But the predictions are saying that in the mid of the 2020s, the electric vehicles can be competitive with the internal combustion engines, and therefore probably we will see much more electric vehicle in the road after mid 2020s. Yeah, I would like to introduce you about the 3 different type of, let's say 3 different main types of the electric vehicles. First one is the battery electric vehicle, which is only, let's say, powered by the electric supply. And as you can see, this is the very simple configuration of the battery electric vehicle. We have one battery source, which is the high voltage battery, and we have inverter to control the e-machine, and we have the reducer and differential to deliver torque to wheels. And mainly average range is between 100 and 200 kilometers for one charge in the electric vehicles for now. But you know, the upper segment, there are range between 300 and 500 kilometers in single charge. But as I said, it's just the upper segment vehicles. And yeah, main advantage of the BEVs is they are not producing any greenhouse gas, and therefore we can say that this is the most environmental friendly transportation vehicle in our lives. And therefore, and also there is no noise in this type of a vehicle, and it's also quite environment friendly. And hybrid electric vehicles, what is the differences between hybrid cars and the battery electric cars? Mainly, hybrid cars have both internal combustion engine and e-drive system. And yeah, this is the little bit more complex system, the battery electric vehicle, because you need to control the driver command by using 2 different engine, I mean the internal combustion engine and e-machine. Therefore, you need more, let's say, complex system. But the advantage is you also reduce the fuel consumption because you can use only e-drive for this type of a car, but a limited range. But yeah, I think this type of a car is like a little bridge between internal combustion engines and the battery electric vehicles. And today it's the most popular type of electric vehicle in the road. And the plug-in hybrid vehicles, these are the, let's say, difference between plug-in hybrid vehicle and hybrid vehicle is this: you can externally charge the plug-in hybrid vehicle by using charging port, and they have more battery capacity than the hybrid vehicles, and therefore you can use more electrical energy, and therefore this is more environmental friendly than the hybrid electric vehicles. I would like to actually explain you what is the aim of this project and why we implement this methodology to our vehicle. Mainly, the electric vehicle manufacturers and developers need to implement many tests to vehicle before they available for product. That means the manufacturers need to implement vehicle testing or different type of testing to vehicle before they then produced product. And one of the important of these let's say tests is the implementation of the driving cycles in the chassis dyno. As you can see in the right hand side, this is the chassis dyno that we can implement different driving cycles to vehicle, and we can simulate the different road conditions in the vehicle. And we can measure the performance of the vehicle, we can measure the consumption of the vehicle and different parameters. But as you can see, there is one chassis dyno, and below of the page we can control the vehicle by using these monitors in real time. That means we can check all different data, and we can also send the different data to vehicle to simulate different conditions. But the problem is this, let's say, chassis dynos or the control room compatible with only internal combustion engine vehicles. That means we in our case we have the battery electric vehicle, but when we connect this vehicle to chassis dyno, we cannot reach data with these monitors. Therefore, we need to connect our computer with the vehicle by using some cables. And if you think like this one test cycle takes 20 minutes, and if you implement 10 different tests in the one day, that means you need to spend 4 hours for inside of the vehicle without doing anything. I mean, you just need to record data by using cable with your computer. And we decided to implement different wireless, let's say, communication between control room and the vehicle. And we let's say implemented wireless gateway we integrated gateway to vehicle and also these computers, and we try to, let's say, control and also receive and send data to let's say between vehicle and control room wirelessly. And I will also present you the integration process, and also the test and performance result will be there in this presentation. Firstly, I would like to talk about the network architecture because the vehicles, the vehicles are much smarter than maybe 10 years in the previous 10 years in the vehicle. And there are many control units, sensors, actuators, smart device in the vehicle, and these devices need to communicate with each other. And therefore, in the automotive industry, there are main 4 different communication protocol we are using, and these are line, CAN protocol, FlexRay, and MOST. Main differences between these protocols are, let's say, bit rates. LIN communication protocol, it's up to 20 kilobit per second. CAN protocol is up to 1 megabit per second. And this is the most common protocol that we are using in the vehicle. And for upper segment vehicle, there can be some FlexRay, and most is more over than the 1 megabit per second. And also there should be some network topology between control units, because you need to connect control unit with cables, and there should be some different topology according to your architecture. And there are main 3 different topology in the industry. One of this is the ring topology. As you can see, there is only one single one-way data flow, and it's easy to manage because you just need to send data to another control unit. You don't need to route any signal to other, and therefore it's easy to manage. But if you have any problem in for example, in this line, the all communication line will have problem, because it's just a single data flow, and there should be some, let's say, it's not a let's say flexible structure to use in the vehicle. And the start topology, we have one central control unit, which is transmitting and receiving different signals from different control units and routing these signals to different control units. It's let's say the adding or removing control units. It's very easy to adapt this type of topology. And yeah, the main disadvantage is this using some the cost side, because the cables, there are more cables than the other topologies, and this is not a good option for the manufacturer when you increase the cost. And also the bus topology, this is the most common, let's say, topologies that we are using in the industry, and there is a bidirectional signal flow, and also this is the flexible structure, because you can just add and remove the control unit whatever you want. And the right hand side, this is our, let's say, topology of the vehicle that we used in this research. We have 3 different CAN lines, and it's up to 500 kilobit per second. And we have also one in line which we are control the compressors and pumps in the vehicle. Mainly, maybe I can explain much detail about the CAN protocol. Mainly, the CAN protocol is the most.
Excuse me, you have 5 minutes left.
Oh, okay. Maybe I can skip that.
Yes, you can maybe go faster.
Okay. About the integration part, this let's say that this right hand side showing the vehicle, and the main idea to integrate the wireless gateway to vehicle by using OBD connector, and we can communicate with these control units with wireless gateway. And the outside of the vehicle, we have a control room, we have another wireless gateway, and our aim to, let's say, receive and transmit data by wirelessly between 2 wireless gateway and control the computer with this vehicle. And the before integration to vehicle, we need to implement these, let's say, idea in the test bench. We simulate the vehicle in test bench, and we saw that we can easily implement this wireless gateway to vehicle, and we can receive and transmit data wirelessly. About the test cycle, as I mentioned, that there is a more, let's say, most common test cycle, which called the NADC. Around this, as I said, this is around the 20 minutes, and it's around 11 kilometers, and that's the distance traveled that by vehicle. Average speed is the 33.6 kilometers per hour, and there are the urban phase and extra urban phase that you can simulate the different scenarios in the vehicle. And also its vehicle is maximum speed is up to 120 kilometers per hour. And when we implemented this system, in the red lines is showing the vehicle speed that we received by wirelessly, and the blue lines is showing the reference speed that we received data by using some cables. And when we compare the system with the older system, our accuracy is the 94.09%, which is saying that the sensor characteristic is quite same, but there should be some delays or noise in the signal, but it's also acceptable for us. And also you can see the SOC level of the vehicle during test, and also the electrical torque of the test of the e-machine during test. And we implemented different scenarios to check our methodology between the range. We have 3 different scenarios, which is first one is the 3 meter, and second one is the 7 meter, and the third one is the 10 meter. And we use the spectrum analyzer to check the, let's say, communication quality between these 2 wireless gateway. And when we implement the 3 meter to between control room and the vehicle, our result is the 26 megabit per second. That means, as I mentioned, the CAN protocols up to 1 megabit per second, and it's quite okay for us to receive and send data in this channel capacity, because you know, we just connected the CAN lines, and it's maybe 26 times more than the channel capacity. And when we implement the 7 meters, it's the channel capacity is 16.6 megabit per second. And when we implement the 10 meters, the channel capacity is 15.8 megabit per second. As a conclusion, what we did, mainly we implemented the wireless gateway to receive and send data and control the vehicle wirelessly. And our, let's say, accuracy is up to 94%. And after that, we implemented 3 different scenarios to check our, let's say, implementation. And our channel capacity is quite okay for different 2 scenarios. And actually, what we did mainly, what we saved the time, because as I mentioned, we need to use maybe 3 or 4 hours per day without the computer. And for now, we just let's say, we can real-time monitor the vehicle by wirelessly, and we can control the vehicle. Therefore, it's a quite efficient way to implementing testing to vehicles. And yeah, thank you for the listening. I think I'm a little bit out of scope of this group, because I think it's a little bit electric machine focused, but I mean, maybe the most let's say, maybe the only group that I can be part is this group. I don't know. Thank you for listening.
Thank you very much for the nice presentation. Yes, it is related to communication, but it's also related to electrical vehicles. So maybe, as you said, you fitted in that group as a result. And yes, we are just running out of the time, and a little bit over the time we are allocated. Thank you very much for the presentation. I don't see any question written on the board, and I don't have one either, so we can pass to another presentation. Thank you.
Thank you.
Our last presentation, ID is 90.
Yes.
The type, yes, the presenter Ileana Diana Nicolai is also one of the author of the paper. The title of the paper is Estimating the Ratio of Kinetic Energy Turned into Regenerated Electric Active Energy through Regenerative Break-in-Bind Electric Locomotive. The authors are Ileana Diana Nicolai, Petre-Marian Nicolai from University of Craiova, Romania, Radu Zlatian Alexandru Netoidu from SC Softronic SA, Romania. Our presenter Ileana Diana Nicolai, could you please upload your presentation?
Yes.
And you can start introducing yourself briefly. Thank you.
I hope you can see it.
Right now, no. Yes, we can see it.
So I am an associate professor at the computer science department at the University of Craiova. The second author is with the electrical engineering department, is my husband. And the remaining 2 authors are with Softronic. They are the major beneficial of the results of this research. So the paper is structured on 5 sections. introduction, operational context, and the data used for analysis, selecting the data associated to regenerative braking, preliminary and final results, and to end conclusions. As an introduction, everyone knows that the study of efficiency of any equipment, and especially at freight electric locomotives, is an actual problem. They are submitted to different modes of operation. We were concerned with this matter this spring. We communicated another paper which addressed the evaluation of the ratio between the regenerated active energy and absorbed active energy in different geographical tractive masses, weather conditions, and driving context. And it was a lesson that we learned, that we have also to compute to have a better picture of what happens. The ratio between the kinetic energy, which can be regenerated, the denominated is the regenerated active electric energy. I present here a brief description of what we expect to get in a traction power supply system. If it has a good receptivity, you can wait for 75% of kinetic energy to be returned to the traction power supply system. Even if 15 propulsion system inefficiency, 55% auxiliary energy consumption, and 5% unrecovered are allowed. And this is a brief description, which are the main actors who are influencing how to compute this, with energy consumption to reach a certain kinetic energy, with the energy consumption considering, I hope you can hear me. Do you?
Yes, we can hear you. Yes, we can hear you.
Sorry, I missed the panel list. The energy consumption considering loss is equal to 25%, and the energy recovered through the traction power supply system. We have a 75% here, but I mentioned it in red because it is not always the perfect system receptivity available. Also, the energy losses in the power supply system, few percent, and the train resistance should be taken into account. Now, which is the operational context of the data we acquired and we are discussing now? The Swedish operator of the locomotives named Lemma, they are submitted to an innovation process through this project, are used to, these locomotives are used to track freight trains in round trips. I hope you can see in the right top corner, which is the scenario. They go from the southwest part. It is a factory to manufacture iron ore. They go to Lale in the right top corner, where the mine of iron ore is. So they go to north empty and they go back with the iron ore. We made studies differently on the going route Borlänge to Lale. It is S1 and the other one is S2. The analyzed route is characterized by high variations of declivity. We will present them later, and sudden direction changes across the route. Some of our previous studies resulted in the evaluation of the mean values for the active energy regeneration coefficient. It was computed all around the year 2020. You have the data here. There are 12 values. considering the months of the year, and the worst values are obtained in the months of November and December. So we addressed this month of November. This study addresses a tandem consisting of two Lemma locomotives. These are the indicators MB001 and MB003. These are the number of carriages, the weights, because we are addressing kinetic energy, data work. So which are the main data which are present interest for us: altitude, regenerated active energies, and speeds. Here it is an example of data we processed. Each other 5 minutes, the onboard recording equipment provides data about latitude, longitude, altitude, active and reactive energy, active and reactive regenerated energy. You can notice that not all values are non-zero, and current and voltage values, average values, along with the speed, which also is important for us. Here you have a plot of the active regenerated energy. It has good, nice segments. Also, it has 0 segments because not always we can regenerate energy. How did we select the data to make our computation? The first step consisting in selecting only the points associated to the regenerative braking. So we got a first set B1 for the first locomotive and the second set B3 for the other locomotive. All the points are associated with strictly positive regenerated active energy. So we restricted the number of points, as you can see. In the left part, it is for the sense of traveling from south to north, and the reverse is in the right part. As I told you, the altitude is highly variable. You start from south, from 100, going down, getting down, and to an end, the mine is placed at 0 nearby the sea. And the speeds are also variable. You can see that it is somehow in mirror as relative to altitudes, but it is not the same number of points because it is not a regular timetable. And as long as you do not have a fixed interval for travel, you cannot have a number of every 5 minutes to constant. The next step after this was to determine another 2 sets, N1 and N3. A point in such set, it is in the previously mentioned sets and is characterized by a speed who is not decreasing but increasing. So it means the kinetic energy looks like being lost, not lost, but increased during the analyzed segment. You have here, it is not a Christmas tree in the right part. It is just we intended to give some explanations for what happened here with stars. You can notice it is up the regenerated active energy. They are the highest values and are associated to small differences between speeds. You can see them. The speeds, you can see them. The speed is increasing, not decreasing, but high differences between the altitudes of the extreme point of the segment. The rhombs denote another situation in which we have equal altitudes in a pair. Such pair, it is the current analyzed point, the one with non-zero regenerated energy, and the neighbor, his neighbor from the left side. So when ROMs equal altitudes, perhaps we had short-lasting regenerative breakings followed by acceleration. So at the end of the interval, we got a speed higher than that from the beginning. Also, I used rand pentagons from time to time to see that they are signalizing a zero difference in kinetic energy. But in this point, either potential energy was lost and turned into regenerative energy, or the small ascending is accompanied by a small value of regenerated energy. Also, I used rectangles where the difference in speed is more significant. It is a small difference in height. They correspond to very small values for the regenerated active energy. Perhaps it was a very dynamic regime with a very short period with regenerative braking and aggressive acceleration toward the end of the interval. Also, circles all over the picture for moderate difference in speeds and up to 40 meters difference in heights. This is the case for non-negligible regenerative breakings. Some of them possibly were caused by railway signalization systems. They were alternating with acceleration such as to get an optimal speed despite the overall climbing operational regime. The remaining points, which have no mark, correspond to descending regimes. So these data sets have 54 points in one of the 6 sets that we analyzed. They represent 39% from the size of the sets B1 and B3 that were filtered first. So we got another set of smaller number of points, BV1 and BV2. The third filtering was needed in order to eliminate the influence of the potential energy variations within an analyzed segment of route. We could not use the flat route condition because only 2 points after those hundreds had difference in altitudes lower than 20 meters relative to their left neighboring point. So we had to use 2 altitude thresholds between adjacent points, 25 meters in the left part, 35 meters in the right part. After this final filtering, you can see we have more points when considering a higher threshold. We got this number of points. Again, in up we can see the speeds in the current point and the left point from it, altitudes on the same idea, regenerated active energies. I used this pair of bars because always one of the locomotives, MB 4001, was better in providing regenerated active energy. Preliminary and final results. First, we had to perform an intersection to avoid the errors coming from 2 different locomotives. So this is the set of data BVA that we were using now. What did we have to do? To compute the tandem's regenerative active energy as the sum for each of the locomotives, to compute the lost kinetic energy in the point I related to the previous point, because we knew the mass of the locomotives and the cars with and without iron ore. Afterward, we compute the ratio of recovered kinetic energy as the ratio between the regenerated active energy and the difference in the kinetic energy, and compute the average of this index across the set, separate for both sense. And we could not use the data that we got in a first instance because we found some deviant values. And so we expected a range of values from 0.45 to 0.85, such as to meet the information we had from the first slide. So we need to filter the results. The scope was to eliminate the recording errors, the influence of potential energy variation, and the segments in which the speeds were too low to allow for regenerative braking. In the left part, you can see the case of lowest ratios under the value of 0.45. Again, I used some markers. Circles are mentioning the cases when braking was used for the train final stop. Within such segments, the speeds became too low to allow for regenerative braking. Afterward, we used rectangles. The deceleration was made towards speeds which were also too small to allow for the same regenerative braking, or there were cases where the gravitation had to be defeated because we could not go lower than 25 meters of difference of altitude. And ROMs were used for the difference between speeds from the segment boundaries when it is very small. This is a very small difference between them. This may reflect small periods of deceleration alternating with periods of acceleration. And again, for these cases too, the train was climbing. And with star, we have a single star. Both speeds from the segment boundaries were too small to allow for regenerative braking. And finally, for the highest ratio, it is clear the first value is a recording error and we have to remove it. And in all the other cases, the altitudes, it was a difference of altitude between the left and the right point. It means the potential energy influenced the results. The conclusions of the analysis, it was that we had to eliminate these deviant values. Then we ran the programs for sets of data on both, 3 sets of data on both senses of traveling. And we got this value for the 3 sets, an average of 0.58 on S1 and 0.59 on the set S2, where the accepted altitude threshold is a little bit higher. These are very similar, very close to that 0.62 we mentioned in the first slide. So we could draw the conclusion that an algorithm was conceived for the determination of the ratio of kinetic energy turned into regenerated electric active energy by using regenerative braking on real operating regimes. Input data were acquired from an onboard equipment every 5 minutes from a non-flat route. We analyzed sets from 3 round trips with highly variable geographical characteristics and the difference between rolling stocks weights. In a single sense, the train cars are empty, the sense S1, and in the other sense, they are carrying iron ore. 3 criteria were used, firstly, to select eligible input data: strict positive regenerated active energy, a speed lower than that acquired 5 minutes ago, and a maximum altitude variation of 25 to 35 meters. And the eligible points were used to compute first estimations, but they had to be filtered again due to the variability of altitude between consecutive points, different operating regimes. Some of them did not allow the regenerative braking, and possible test errors. You might recall that we had to make a difference between the eligible points and the ones with deviations, and we got very good results for the capability of the analyzed tandem with respect to transforming kinetic energy to regenerated active energy, and validate the usability of algorithm on real data because it does not impose the using of a flat route. Thank you for your attention. And yes, this paper perhaps is suitable to present for data mining. It has
Thank you very much.
Thank you.
Thank you very much for the nice presentation. It is very important to derive these points and to filter, to classify. It is really interesting how we approach. So thank you very much. We are end of the Electrical Machines-2 session of 13th International Conference on Electrical and Electronics Engineering. Thank you very much for your attendance. I wish we could host all of you in Bursa. And also I would like to take this opportunity to thank the ELOCO President, Professor Dr. Can Kalenderli, and ELOCO team for inviting me as the sessions chair and organizing this conference. Thank you very much. See you in the next session. Thank you.
Just a moment.
Yes.
My husband, the second author, wants to say you some words.
Yes, please.
Yes, about the last paper, I have a special mention. We developed with the Softronic company, which is a company who produce electric trains, a big contract financed by European Union for the last 5 years. One of the objective of this contract was to how to register the energy and how to recovering, and finally how to put this in a legislation, because recuperate the energy, the regenerative processes are not registered by the company who will supply the lines. So it's a problem at the European level, not only in Romanian, how to pay the electric energy as a difference between the consumed energy and the recuperate of the electrical energy. So it's a big problem, probably also in Turkey. Maybe we'll collaborate with some companies from your country, very nice country. And we developed a train with light traction. Now, in this contract, it's a good opportunity to have a train for 200 kilometers per hour for the places where is not big differences between flat routes. Thank you.
Thank you very much. Yes, you pointed out it is a big problem how to separate them, how it is consumptive one and regenerated one, and how they are gonna put the value. So it is really important subject. Yes, there could be some collaboration maybe in the future. Thank you very much for your attendance again.
Thank you.
And this is the closure of the session. Have a nice day. See you in the next session.
Thank you.
Bye-bye. Thank you.